The objectives. Graph functions expressed symbolically and show key features of the graph by hand in simple cases and using technology for more complicated cases. You must be able to graph exponential and logarithmic functions showing intercepts in end behavior and trigonometric functions showing period, midline, and amplitude. We are working toward that. Understand radian measure of an angle as the length of the arc on the unit circle subtended by the angle, and explain how the unit circle in the coordinate plane enables the extension of trigonometric functions to all real numbers, interpreted as radian measures of angles, traversed counterclockwise around the unit circle. Starting off here with the opening exercise. The height and co-height functions of a Ferris wheel. We've done the height already. Today we are doing the co-height. And this says, for the opening exercise, suppose a Ferris wheel has a radius of 50 feet. We will measure the height of a passenger car that starts in the 3 o'clock position with respect to the horizontal line through the center of the wheel. That is, we consider the height of the passenger car at the outset of the problem after 0 degrees rotation to be 0 feet. This is the 3 o'clock position, just like a clock. 0 degree rotation, that's where we're starting at here. And we're considering that height to be 0 feet. Last week we considered that to be 50 feet if the wheel were 100 feet tall, because half of that is the radius, and that is clearly 50 feet above the ground. But now, this week, this is now 0 feet. Mark the diagram to show the position of a passenger car at 30-degree intervals as it rotates counterclockwise around the Ferris wheel. So part A, mark the diagram to show the position of the passenger car at 30-degree intervals as it rotates counterclockwise around the Ferris wheel. 30-degree intervals will be like this, and you're fortunate enough to have yours already marked off. And I'm doing mine by hand, so yours is probably going to be more accurate than mine. So we'll confer with you before we come up with a final one. Okay, so the height of the Ferris wheel, it's at 0 degrees right now. What is the height of that passenger car at 0 degrees? It is not 50 feet. Let's go back up here into the thing. It says right here, that is, after a 0 degree rotation, it will be 50 feet at the horizontal line, or 0 feet at the horizontal line. Therefore, the height of this passenger car now is what? 0. So down here, we would mark a 0. At 0 degrees, it is 0 feet. You can try to replicate this graph accordingly. You only need an x-axis, a y-axis that meet at this point, and note that this is h for height, and this is DEG for degrees. Use one block per 30 degrees, so you do not have to write all of these down. Just as needed as we go along. We turned and came up with no turn, and we came up with 0 feet. So now we're coming up here at 30 degrees. So at 30 degrees, what is the height? Approximately. You don't have to get too into it. Just an estimation. Mine looks like it's about 42. What does yours look like for the height? 45. I have 42. Anybody else have something different? Okay, so we'll go with 42. We'll just mark 42. And at a 30-degree turn, we came up with 42. Now, is that the height of the passenger car? Yes or no? Where did I get 42 from? Is this the true height of the passenger car? No, why not? Does this line here represent the height of anything? No, it's how many feet? 0. So which axis would I have to use to measure the height of the passenger car? The y-axis, yes. So we would be coming this way. So what is that height? Mine looks like it's about 25. What does yours look like? I hear another 25. Anybody have something different? Okay, so it will be 25. So notice that you don't use the x-axis to measure height. You're using the y-axis. So we erase that dot and we come down here for this, and for 30 degrees we're putting a 25-foot marking. Alright, back to the wheel. We come out this way and we'll go in blue. We go to 60 degrees and we're looking for the height. Mine looks like it could be about 43. What does yours look like? Anybody have something different than 43? $45, so we'll go with 45. So at 60 degrees we will have 45. What should the height of the car be when it is at 90 degrees? 50 feet, right. So we'll come back down here and do 50 feet for 90 degrees. Since we're going in 30-degree increments, we're going to go here to 120. Would the height of the car at 120 be the same as the height of the car at 60? Yes, from there to there. So what we put down before was what, 45 or was it 42? We used 45? Okay, so we'll go at 120 and mark a 45. Should it be the same for 150 as it was for 30? And for 30 we used what measurement? 25. My dot's a little bit off there, so I'll mark that. And 150, 25. So next up is 180. What is the height of the car at 180? 0. So we'll come back down here to 180 and make a 0. Next up is 210. Would the height of the car here be the same as it was for this one here? Of course, mine is free-handed, so would it be the same? It would be the negative version of it. Okay, so we would have a negative 25. Then would we come up with another 45? Did we use 42 or 45? I don't think it's going to matter in this example, but I think we use 45. So we would go to 240 and do a negative 45. And at 270, notice that 270 is directly at the bottom. What is the height? Not 0. Negative 50, yes. And then we continue back up. Negative 45, negative 25, and then on the way back to 360. So look what has happened. Compare that to what we did last week, where it all stayed above 0 and you went from 0 up to the highest point, back down to 0, back up, back down, a roller coaster effect. This one is the same principle, but it looks a little different. It's dipping down below 0. Explain how you can identify the radius of the wheel from the graph in Part B. And here is the graph from Part B, roughly drawn. How could you identify the radius by looking at only the graph of the movement of the passenger car? Yes. That's right. You can get a maximum point. That would be the highest point that it goes to, and then a minimum point, the lowest point it reaches. If you use this down here as your radius, notice that it will not be negative 50 as for the radius. A circle doesn't have a negative radius, so you would just simply change it to positive. If you use this one, you just keep the positive value. Here is another question pertaining to the Ferris wheel, in which the radius is 50 feet, just like the one we did. If the center of the wheel is 55 feet above the ground, then how far above the ground would the car be if it's at the top of the wheel? The radius is still 50 feet for the Ferris wheel, but it's 5 feet off the ground at the bottom. It would be 105 feet off of the ground, yes. Is there another measurement we can model as the function of degrees rotated counterclockwise from the car's starting position? Remember, we have done this so far. Last week, if we came up to here and made a triangle, we knew the degree measurements, let's say 45 degrees. We solved for this height. We measured from here to there, and we added it to the radius so we could get the true height above the ground. Today, we measured only the height of the car, with this being 0, and we used these markings to measure the height above the horizontal line. Is there another marking that we can use? You can measure the horizontal position of the passenger cars. When we used the x-axis, we were measuring the vertical position. Now you can measure the horizontal position there. Or actually, we were using the y-axis to measure this. That's the height of the car. Now what we are doing is we can use the x-axis. We're measuring the car in relation to the y-axis. So that is the horizontal position. This is the horizontal axis. So the car will have a horizontal position here on this axis. We used the y-axis to measure height this way. But now we're going to measure the position from the car to the y-axis. That is the horizontal position. How should we measure the horizontal distance? In other words, what markings are we going to use to measure the horizontal distance, for example, from there to there or from here to there? Would we be using the x-axis or the y-axis? The x-axis, yes. You can measure the horizontal displacement through the vertical line through the center of the wheel by using this axis. You are going to call that placement the co-height. So before we had this, we called this the height. When we go from here to there, we are going to call that the co-height. Where is the car on this circle when the co-height is 0. It is on the x-axis, right. Is that true or not? Your first initial thought might be yes, but what is the distance from this car to the y-axis there? What is the distance from right here to this point? 50. So is the co-height 0 there? The co-height is the distance from here to this. It's 50, yes, but we need to know where the co-height is 0. At where? We're moving this direction. Tell me when the co-height is 0. At the top, it would be 0. We're moving down here. What would the co-height be? Negative 50. We're moving down to here. What is the co-height? 0. And what is the co-height here? 50. Remember, it is the distance from here in. If the car is here, it's the distance here in. And when it's on the y-axis, there is no distance to measure. It is 0. So the car is along the vertical line through the center of the wheel. So it is either at the top or the bottom of the wheel where it is 0. How can we assign positive and negative values to the co-height? In other words, what sign is the co-height when it's in this area? Positive. What is it when it's in this area? Negative. What is it when it's in this area? And in this area? Positive. Assign a positive value for positions on the right. So if you're on the right, you're positive. If you're on the left, you're negative. What is the starting value of the co-height? 50, yes. And that's in this example only. It'll just be the radius for whatever problem you happen to be doing at that time. Since the radius of the wheel is 50, then the initial co-height at the 3 o'clock position is 50. Suppose the passenger car has rotated 90 degrees counterclockwise from 3 o'clock. And here's where it ends up. What is the co-height? 0. Is there a maximum value of the co-height, and is there a minimum value? What is the maximum value? 50, and what is the minimum? Negative 50. Exercises 1 through 3. Each point, P1 through P8 on the circle in the diagram at the right represents a passenger car on the Ferris wheel. What do you immediately recognize about the passenger cars on the Ferris wheel that is different from the problems that we have done before? They're scattered. There's no consistency with their placement. Therefore, Section A is to draw segments that represent the co-height of each car. Which cars have a positive co-height and which cars have a negative co-height. So here are the segments to represent the co-height of each car. Okay, now that we've done that, which ones are positive? Which ones have a positive co-height? 1, 2, 7, and 8. All right, so we list those 1, 2, 7, and 8. Which ones have a negative co-height? 3, 4, 5, and 6. Right. The next piece is list the points in order of increasing co-height. That is, list the point with the smallest co-height first and the point with the largest co-height last. And we will do this off to the side over here, top to bottom, starting with the least co-height. P5 is the least. It is clear out here, and remember these values are what? negative, and this one is the furthest out. So P5 has the least value for a coheight. What is the next one? P4. So we've done 5 and 4. So there's P4. What is the next one? P3. The next one? P6. The next one? P2. P7. P1. And P8. With P5 being the smallest and P8 being the greatest. I'll zoom in on this as I read it. Suppose that the radius of a Ferris wheel is 100 feet. We can draw a Ferris wheel. The radius of the wheel is 100 feet. And the wheel rotates counterclockwise through one turn. So it's going this way. One turn. Define a function that measures the coheight of a passenger car as a function of the degrees of rotation from the initial 3 o'clock position. Here's the 3 o'clock position. The first question is, part A, what is the domain of the coheight function? In general, you have to remember this. If you have a function f of x, it will spit out a value of y. So whatever I'm putting into this is the domain. Whatever comes out is the y. What is the one piece of information that we always have for a car on a Ferris wheel? We don't know the height, we don't know anything yet, but we do start off knowing its placement, and that placement is measured in terms of what? Degrees. So you put in degrees into the function, and whatever you put into the function, that is the domain. The domain has a least value and a highest value, even if it's negative infinity up to positive infinity. But in terms of degrees, we are starting at what degree on the Ferris wheel? 0, and with one turn of it we go up to our highest degree value of what? I'm hearing tentative, nervous answers. Well, if we go through one turn, how many degrees is it? 360, yes. There is your domain. Whatever degree value you enter in on there, you're going to come back with a coheight in this case. So we put in a degree, and what it's going to spit out is a coheight, the measure of the car back to the y-axis. What is the range of the coheight of the function? Look at your wheel, and I will redraw it again. Here is the Ferris wheel, and it said up here in the directions that the radius of a Ferris wheel is 100 feet. So if it's 100 feet for a radius, we need to generate the coheight function. In other words, we start at a certain amount and we can go back to another amount, or what is our least amount up to our highest amount. What is the least amount for the coheight for a Ferris wheel that has a radius of 100 feet? Negative 100. What is the highest? 100. There is your range. That is what can be spit out. No matter what domain value of degrees you plug in, the value you get out will be between negative 100 and positive 100. How does changing the wheel's radius affect the domain and range of the coheight function? So let's go back and revisit the domain. The domain was from 0 to 360. If I change the radius, does it affect the domain at all? No, it does not. Here is the range. And from the problem we just did, it's negative 100 up to 100. How does changing the radius affect the range? It changes the maximum and minimum values. One thing about the range that will not change is that it will still be a negative radius up to a positive radius. That element still stays the same. Your actual numbers will change if your radius changes. For a Ferris wheel of radius 100, I'll zoom in so you can see it as I read it. For a Ferris wheel of radius 100 feet going through one turn, how do the domain and range of the height function compare to the domain and range of the co-height function? Is this true for any Ferris wheel? So for the height function, what we did last week, we had something that went like this and then back up, like this and then back up, and so on. This week, we have something that looks like this. It goes like this, back down, and then back up, and then back down, and so on, drawn freehand without any markings to go off of. I'm just doing this in general. How do those two compare to each other? Yeah, they will have a peak in there that has the same value, but then this one dips down to this. But with this one, notice that you could take this one and flip it up and generate pretty much the same shape. This is your homework before you get your cameras out and start taking pictures like Justin Bieber is standing beside me up here. And take note that you have 5 questions, all of which must be answered. And each of them have more than one part except for number 4. Actually, it does have 2 parts. It's just not broken into A and B. When it's asking, for example, in 1D, explain how you can identify the radius of the wheel from either graph, you must answer that question with a complete sentence. One that starts with a capital letter and ends with a period and has proper punctuation in between where necessary. It must be spelled correctly and it must be legible enough to where it can be read.